Whenever the beam has a uniform cross section, in that case we observe that the bending stress will going to change from the free end to the fixed end in the case of cantilever. How exactly the bending stress will change along the longitudinal axis, that depends upon the type of loading, whether we have a point load or UVL or UVL. According to it, the stress distribution will change. And if the value of the bending stress is remain constant over the entire length, that is along the longitudinal axis, it will be called as the uniform strength of the beam. So in the case of uniform strength, the value of sigma b, that is the maximum value of a bending stress, sigma b maximum, is uniform, that is not a function of x. But if you select a constant cross section of a beam, then the bending stress is a function of x. So how exactly the bending stress will vary along the longitudinal axis? For this case, we'll discuss here a different situation. First, we consider here a beam AB, which one is a cantilever beam, and we have a fixed support at point A, and let's say L is the length of the beam. This time we are using a rectangular section, and everywhere along the longitudinal axis the cross section is uniform. At free end, we'll set the value of x equal to 0, and if we move towards the fixed end, we have positive value of x. Exactly at fixed end, we have x is equal to L. Now the same section we have shown here, this one is representing the point B, this one is representing the point A. At point B, where we have x equal to 0, we have cross section is B multiplied by H. And this cross section at any distance here is also remain same, that is same as equal to B by H. So this cross section at any distance is also constant value. Even at x equal to L, we have a same cross section. So this figure represent here the uniform cross section. If the cross section will not change, in that case the value of Iz as well as the value of C both are constant value. They will not going to vary because of uniform cross section. So somewhere we can locate the value of the centroid here. Perpendicular to this cross section, we have x-axis. This axis is same as our z-axis, and the vertical axis is y-axis. So the maximum value of a bending stress, sigma b maximum, in general is given as m. Now I will write here suffix x because I want to know how the bending stress will change. So bending moment will change as the distance x will change multiplied by the constant c. That is the value of c is same as equal to h by 2. So in this case we have to select the value of c is equal to h by 2 divided by Iz, and the Iz value is also constant value. The maximum value of a bending stress at any section is purely a function of bending moment at that section. So let's consider here one section plane with distance equal to x from point B. So this distance is same as distance x. Bending moment at this point will be equal to the force F multiplied by x. Since here the force is acting on the right hand side of the given section, and for the right hand side we have the sign convention is the downward shear force is positive value and the anti-clockwise moment will be positive value. But for the given section here, this force is making an clockwise moment, so it must be the negative value. So we have mx is same as equal to minus, because it's a clockwise, is force multiplied by x. Now the value of the force is also remain constant here. So if we substitute here mx equal to minus of fx, in that case we have maximum value of a bending stress at any cross section is purely a function of minus f of x. Minus sign doesn't make a difference here. So we have bending stress at any section. So at section B or at point C or at point A, that is what we are calling it. And this maximum is at the top fiber. Is directly proportional to x, but is a negative value. It means that we have to show the bending stress below. So from above equation we conclude here that the bending stress at any location x is a strong function of x. And as the value of x will increase, the bending stress will also increase. At point B we have value of x equal to 0, so bending stress will also equal to 0. So at this point we have maximum value of a bending stress will be equal to 0, and since we have a linear variation, so bending stress will go on increasing as you move from B to A. So this one is representing the bending stress distribution at it is the maximum value at point A. This distribution is simply equal to sigma B max. So this one is nothing but sigma B max is equal to mx can be replaced as minus of f into x multiplied by constant c divided by iz. To find out the bending stress at point A, we have to put the value of x equal to L, and we can find out the maximum bending moment at the fixed end. Now consider again the same rectangular section, but we have changed the beam, and this time we have a cantilever beam and is subjected to uniformly distributed load. And we are interested to know here how the value of bending stress will change along the longitudinal axis. For this one, we'll set up our axis system. At B, we have x is equal to 0. At A, we have x is equal to L. And we'll consider here one section at a distance equal to x from the free end. So we'll consider here one section plane to show the variation of a bending stress, and we'll find out here the value of bending moment at this section. So we'll consider here one section at distance equal to x from the free end B, and we'll calculate the bending moment at this section. Since we have UDL here, so total equivalent load will be acting in a downward direction. So for the distance x, we have equivalent point load acting will be same as equal to W multiplied by x, and is from the section the distance will be equal to x by 2. So this distance is x by 2. In that case, we have bending moment at the given section will be equal to minus W multiplied by x, and further multiplied by distance is x by 2. So we have minus of W into x square divided by 2. So bending moment will continuously vary. It is 0 at point B and it is maximum at point A, but we are not interested in the bending moment. What we are interested in the maximum value of a bending stress. So maximum bending stress at any location x will be given as the moment at that section multiplied by the constant c divided by iz, and this value is same as equal to minus of W into x square divided by 2, further multiplied by c and further divided by iz. It means that a bending stress at any location and the maximum value, which will be either on the top or bottom, is directly proportional to negative of x square. So this one is representing the parabola, and that too particularly the downward parabola. So you have to show here a downward parabola. Bending stress at point B will be 0 and it's a maximum at point A. So this graph indicate here the bending stress sigma B maximum at any distance x is equal to minus of W into constant c divided by 2 times of iz multiplied by distance x square. So in the case of UDL, it will vary parabolically. So whenever we have given the UDL, and that too in cantilever, the bending stress will vary parabolically along the longitudinal axis, and we have maximum value out of all these bending stress will be at the fixed end that equal to A. So these are the general type of questions may be asked in the GATE examination to know the value of the bending stress along the longitudinal axis. Again, we'll take here the third example in which we have a cantilever one point load acting at point C exactly at the center. Now since there is no loading from B to C here, the bending stress will be equal to 0 between B to C. We'll again consider here one uniform cross section having the width equal to B and the height equal to h of a rectangular cross section. For this section, we have iz and c is constant, value of c is same as h by 2, and the bending stress maximum at any location x is given by flexure formula, bending moment at that location multiplied by c divided by iz. So no force is acting between the section of the beam from B to C, so shear force will be 0 and therefore the bending moment will be equal to 0. So for the portion BC here, we have value of bending stress equal to 0, and we are using here the rectangular area. So this area is a useless area, unnecessarily the waste of money. But at point C the force will act, so exactly at point C we have bending moment will be 0. But if you consider any section here at distance equal to x from C, in that case we can calculate this bending moment mx will be same as equal to minus f into x. And if we substitute this value back into the bending stress location, so you will get this value equal to minus of f multiplied by x multiplied by c divided by iz. Minus sign is meaningless here because either of the top or bottom will come in compression or tension. So this time we have the bending stress maximum at any location x is purely a function of x. Purely a function of x means for the portion AC, the bending stress sigma b maximum will vary linearly. So if I want to show the bending stress distribution at C will be 0 and it will go on increasing, and it's a maximum value at point A. So at this point we have maximum value of bending stress sigma b max, and we can obtain this value by putting the value of x is equal to L. And the bending stress we can obtain here using this equation by substituting the value of x equal to L. So in all the three examples that we have discussed right now, that is, in the first example we have cantilever and we have point load. What we observed at the free end, we have bending stress is 0, but we are using the constant area of the beam. Whatever this area is using here is no use. Since here the bending stress at this point is coming out to be 0, we have to actually a 0 area. And then the bending stress is gone increasing towards the A. Means in fact here we want this type of cross section like this one. Now you observe here this cross section here. This cross section is a variable cross section. At tip here we will get a 0 area, and at the fixed end we will get the maximum area. Such type of beam will be called as the uniform strength. Same is the situation in the case of UDL. We have a bending stress equal to 0 and we are using here very large area. So better to use here the variable area. Even in the third figure here we have cantilever, but the point load is acting at the center of the cantilever. So portion BC doesn't have any stress, but for this portion BC we are using here a very large cross section. So this is not a good design practice. You have to design the beam according to the bending stress variation along the longitudinal axis. A cantilever beam has a square cross section of 10 mm by 10 mm as shown in figure. It carries a transverse load of 10 Newton exactly at the half. Considering only the bottom fiber of the beam, the correct representation of the longitudinal variation of the bending stress we have to find out. Either A is correct, B is correct, C is correct, D is correct. This section is a uniform section, and because of uniform section, the value of Iz and the value of C, that is the distance of the top fiber and bottom fiber, in this case will be same. So if I show here the centroid that equal to G, then the value of the top fiber as well as bottom fiber, which is represented by C, is same as equal to 10 divided by 2 is constant value, as well as the value of Iz is also constant, that is not going to vary along the x-axis. So neither the value of C will change, neither the value of Iz will change along the longitudinal axis. So this one is representing here a longitudinal axis. Let's mark here point A at the fixed end, point B where we have point load, and for point C we have the free end. Between B and C here there is no shear force acting, that is no load is acting on B and C. Therefore for the portion BC the bending moment will be equal to 0. So for the section of the beam from B to C here, there is no shear force acts. Bending moment is 0, and if the bending moment is 0, sigma B maximum value is also equal to 0. But for B to A, the bending moment will exist, and the bending moment is a strong function of the distance x from the point load which is acting at point B. So let's consider here one section, and let's say this section at distance equal to x from point B. So at point B we'll set up our x equal to 0. It means that at point A we have x is equal to L. And at the given point here we have the value of bending moment mx will be 10 multiplied by x, but will be negative value. So we have minus 10 into x. So this time the bending moment is a linear function of x. So for section AB here we can calculate the value of bending stress maximum at any location x between AB only is given as bending moment mx multiplied by c, that is the distance of top or bottom fiber, whichever is maximum, this time both are same, and is divided by Iz value. And we can replace the value of mx here equal to minus 10 times of x. So we have minus 10 times x multiplied by c divided by Iz. Clearly here the value of 10, c and Iz is constant. So we can conclude here the bending stress sigma b maximum is directly proportional to minus x. So there is a linear variation of a bending stress. So at A we have x equal to L is equal to 1 meter. So we can calculate the bending stress maximum at location A. That will be equal to minus 10, that is Newton. X is in meter, so you have to multiply by 1000. Distance C will be 10 by 2, so we have 10 divided by 2. For square section, moment of inertia is a to the power 4 by 12. So we have 10 to the power 4 divided by 12 will shift in numerator, and we can find out this value. So this is 10 to the power 3 and this is 10 to the power 4. In that case, this total term is get cancelled with 10 to the power 4. We have 10 into 12 is 120. 120 divided by 2, that will be equal to 60, but negative value. So we have minus 60 megapascal. So there is no stress is acting between B and C. So there is no stress acting between B and C. There is no stress acting. There is no stress acting. But this is 400 and 400, so choice C and choice D goes wrong. This one is a parabolic distribution is only in the case of UDL. It means that this figure is correct. That is the choice A is correct. So for the portion BC, there is no shear force acting, so bending stress equal to 0. So you have to draw here a bending stress equal to 0 level. Then between A and B, we have confirmed it's a linear variation, and we have bending stress maximum at point A equal to minus 60. So you have to show here the 60 megapascal, and you have to join the point A with B with a straight line. So this one is the correct distribution of a bending stress, that is the choice A is correct. So bending stress will change along the longitudinal axis and is 0 from B to C and is maximum at point A, and it will vary in between A and B either linearly. The video you are watching is from the app, which is the Mohod class app available on Google Store. And in this app, we'll cover all subjects involved in mechanical engineering for GATE. Join the course directly from your mobile. The link is given here.